All right, we're gonna get going here. Today's problem, our second to last tree problem, is binary tree maximum path sum. This is the first hard tree problem we've done, and it always kicks my butt. I've done it like 3 times, and we'll see how this goes. Okay, so here's the prompt. It says, given the root of a non-empty binary tree, we want to return the maximum path sum of any non-empty path. And because path can mean so many things, they give us a definition on what they mean by that here. They say a path in a binary tree is a sequence of nodes where each pair of adjacent nodes has an edge connecting them. And then they say a node cannot appear in the sequence more than once. Okay, now the path does not necessarily need to include the root. We'll go through some examples of what makes something a path, because that's actually really, really important for kind of the nature of the solution here. So my connection is really, really bad right now. Let me just see if I can. Okay, it's back to normal. Sweet. Okay, and then this part is a little more straightforward. The path sum of path is just the sum of the nodes in that path. All right, so pretty straightforward on this guy right here. In terms of a path, I'm going to describe this essentially as a set of nodes that has exactly one... Okay, let me back up. I'm going to define a path as a set of connected nodes where only one of those nodes can include both children. Okay, so if we think of it that way, then one path that we can include in this tree right here is 1, 2, and 3. 1 gets both of its children included, 2 and 3 don't. Well, I guess they kind of do because they're both none. So yeah, there's probably a better definition here, but that's effectively the way we can think about it. We'll explore this with a more complex tree in a sec. But the path here is 2 to 1 to 3, or 3 to 1 to 2, and no matter what, the sum is 6, and that's what we end up returning. Okay, here's another significantly more complex example here. This has a solution that is in kind of the same form, which is just 3 connected nodes. But yeah, so we have all of these nodes here. Notice that the values can be negative, and obviously negatives will have a more complex effect on the overall sum. But in this case, the solution that we return is just the sum of these nodes right here, 15, 20, and 5, which makes a total of 40. Notice if we try to include the root here, so let's go through like a couple possibilities. If we included the root and also the left subtree with the 10 here, and the right subtree with the 20, then we would only be able to select one of these children to add on. So one path here could be 10 to negative 15 to 20 to 15. Or we could go 10 to negative 15 to 20 to 15 to negative 5. But notice, like, between those two last ones that I mentioned, so these 4 versus all 5, there's never going to be a good reason to take the negative 5, right? It can only hurt our answer. Regardless, though, when we select all of these, so 20 plus 15 is 35, but then we have plus negative 15, which brings us back down to 20, and then 20 plus 10 is 30. So this is overall a worse sum than just this little subpath right here. Okay, so it's totally possible for us to not select the root at all, right? We might have a section of the tree that is just lower down, and that's our solution. Okay, and again, in terms of like opportunities to select both children, so when we have multiple nodes like negative 15 and 20 that both have a child on both sides, only one node in this path gets to use both children. Okay, yeah, it actually, is that a complete definition for path? Because let me think about this. Yeah, it's really not even that, because like if you think about, for example, negative 15 to 20 to 5 to 15, that wouldn't be a path, because even though only one of them gets both children, because in order to traverse that, you would have to either go like this way or you could go this way, right? So actually both of those fail. So you know what? They've got a good definition for path here. um, yeah, only one of the nodes in the path is allowed to appear. Sorry, no node can appear twice. Okay, and I guess another way to think about this is whichever node does select both children, that has to be the root of the path that you choose. So, okay, there's a more complete definition. We can define it formally as only, or no node can appear twice in the path as you follow it. Or we could say that whichever node has both of its children included, it must be the root of the subtree that comprises the path. Okay, yeah, so if like 5 had a child over here and then it had a child over there, that's totally fine. You know, we could trace it along this way. All right, so a few different ways to think about it, each of them with their own strengths, I guess. But yeah, some important details that we've already observed. We want to be selective about choosing negatives, because, for example, if this had been like 40 right here, then all of a sudden it is actually worth taking a little bit extra parts of this path, right? So it's possible for us to take a path that includes negative nodes if it's worth it for the overall sum, I guess is what I want to say there. So if this had been 40, then the overall path we would have taken is actually 40 to negative 15 to 20 to 15, because it's worth including this little extra part of the subtree. Okay, obviously we need a more like programmatic or more complete way of thinking about that, but we'll keep going to get the rest of the details on the problem, and then we'll explore the solution a little bit. Okay, so constraints, as they told us, it's a non-empty binary tree, so the number of nodes in the tree is at least 1 and up to 1,000, and the values are between negative 1,000 and positive 1,000. I think Python doesn't have real issues with integer overflow anyways, but I think we can expect that this is not going to have weird overflow issues when we create the sum. All right, so let's diagram this a little bit. I'm trying to decide if I want to take this. Yeah, I think we'll use this diagram here. I think it's got enough details for us to work through everything we need. So let me grab this, and then I'm gonna... Oh, that's not what I wanted. Where's the undo button? Yikes. There we go. Okay, let's grab this photo, and then we'll diagram this a little bit. All right. So we got this tree here. Again, we want the maximum path sum, and the idea is that we want to consider the possibility of any particular node being kind of the root of the optimal path. It's possible for us to improve upon it later, but since only one node in the final solution can have both children and it has to be the root, we can kind of pass that information along and then think about, okay, like what if this isn't the root of the tree? Then we just need to pass it upward. We need to pass the information upward to see if there is a better root somewhere higher up in the tree. Okay, so yeah, I'm trying to think about how to phrase this in terms of the recursion that we have to kind of inevitably do. So in terms of what's going to get passed up, we want to tell higher nodes, hey, here's the best I can do without branching. So for example, for the 20 node, we want to tell the negative 15 node, hey, assuming that I am not the root, here's the best that I can do without branching so that you can try and be the root. If you do better than me, then we'll keep that. If you can't do better than me, we'll just keep what I did, basically. Okay, so what we're going to want to do is somewhere off to the side, we're going to want to store like what I'll call branching max. So this is like out of all of the possible root nodes for the optimal path that we've seen so far, what's the best that we can do? Okay, and we'll overwrite this repeatedly, so this will be sort of separate from the recursion. We'll just store it as maybe a class variable or like a function variable if we write a helper function, and we'll just kind of update this as we go for considering all of the nodes as the root. So like if this guy's the root, what's the best that we can do? That'll get stored in here. And then we'll say, hey, okay, now let's say we can't branch. Okay, this is the best that we can do. We'll pass that back up to -15, and we'll try and use this as the root instead, right? In which case it'll go like that. And if that's better, then we'll store that in this variable. Okay, so we have sort of a running maximum that is considering every node as a possible root of the optimal path. Obviously, they won't all be optimal, so we need to update that as we go. Okay, and then what else do we need again to pass, or what we need to pass up from layer to layer is what's the best that I can do without branching. So assuming I can only take one path or one side at a time, what's the best I can do with that? Let me pass it to you, and then let me pass it to you over here. And we'll use those non-branching sums to figure out, okay, what if this guy is the root? Well, then the best possible sum we can get is the best on the left plus the best on the right plus the root, in terms of if this is the root, right? If this is the optimal root. Okay, so that's the overall like gist of the solution. So the recursion here is basically like, what's the best I can do if this is the root and I am allowed to branch. I'll put that in branching max, assuming that it is the best we've seen so far. Okay. And then what we need to pass upward is what is the best I can do without branching, right? On the left subtree and the right subtree. Okay, and then, so again, so many details here. I think two last considerations we need to make. If we are passing up a negative, there's pretty much never going to be a reason to take that. So like, for example, when we get to 15, when we're considering this as the root node, we get a left sum and a right sum without branching. Well, the left sum is -5, but there's no reason for us to ever take a negative like that. If we're considering 15 as the root node, then let's just never take this and only take what's on the right because it's 0. But if there were other nodes, we would want to take that, right? And that's kind of handled, well, earlier I mentioned, hey, well, what if there is a negative, but it's followed by a positive and it becomes worth it to take it? Well, let's consider what that would look like. If we had another node here that was like 30, well, this guy passes 30 up, and then this guy passes 25 up, right? Because that's the best we can do without branching. So assuming that there is like a later node that makes it worth it to take this path, we'll see it because it's not just this node we're passing up, it's the sum of all the non-branching paths below that node as well. Okay. Last consideration here is what is the base case? I think the base case, the easiest one, and this is a pretty common one we've used so far, is when we get to a none node, well, the sum for a none node is just 0 because there's nothing there, right? It has no effect on the sum. All right, and I think that's about it. I haven't really written down much here, but this is, again, kind of, we've been talking about recursion for pretty much all of these tree problems. We are basically just trying to answer for every subtree here. So like if we have this subtree and this subtree, so for any particular node, the first thing we want to do, well, okay, actually, yeah, the first thing we want to do is calculate the left subtree's maximum path sum. That's going to be recursion, right? And let me even specify left subtree's maximum path sum, no branching. So the branching stuff is going to be stored again in this separate like non-local variable here. Okay, the next thing we need to find is the right subtree. I wrote tree when I said subtree. The right subtree's maximum path sum with no branching. Okay, the next thing we're going to do is consider the root as the root of the optimal subtree. Okay, so this is going to say, hey, add up the best you can do on the left, the best you can do on the right without branching, and me. If that's the best we've seen so far, put it in here. Right. Okay, and then finally, we want to return the best we can do with no branching, so that the next node above us can use that as part of their solution. Okay, and I guess the 0 we should say here is if we get none, we should return 0. Because we already know that's a trivial answer, right? It's one that we'll always have without needing to make any additional calculations. All right, if I remember correctly, the big pain in my butt for this problem is how to deal with the negatives. Like there's specific places where it makes sense to like replace them with 0 basically is how we're gonna do it. So like maximum between the value and 0. So we'll see if this works, but this is the overall algorithm. Let me think about if I'm missing anything here. Not especially. I might think of things as we go, but definitely this overall pattern of like base case. In fact, I'll even kind of mark this up here because this is how we've been doing all the tree problems, is like, what's the base case? Like, what are the left and right subtree sub-problems? Like, how do I handle the self node? And then, like, what do I return is the last question. So fundamentally, I think every tree problem that we've done boils down to this pattern, with the final question being like, what order should we do this in? Sometimes we need information from the two subproblems first. Sometimes we want to handle the self first. We've had different problems that require different orderings, but it's always like these core components. And then just like assembling them for the self node. All right, let's see how this goes. No promises, to be honest with you. This might be really bad. What was I opening? Oh, yeah. Oh, that's not what I wanted. Okay, wait, I'm gonna do this, I'm gonna split view, and then I'm gonna open this up. Nice. All right. Okay, so we want the max path sum. When we, okay, so we already know that it returns an int. We want to, again, store the branching max as, we could either store it as a class variable, or we could just store it as a solution, or as a, like, a variable inherent to the function. I'm gonna say, ooh, actually, is this something we can do? Yeah, we can. I think we should be able to manipulate this. Okay, so we can say self.branching max. Now we want this to lose immediately. As soon as there's something better than this, we want it to be replaced, right? There's two main ways we can do this. We were given the constraint that the values are between -1,000 and +1,000, so we could make it like -1,001. That is a little bit magic numbery, so instead we could say, let's set it to float -infinity to start with. And this is just going to guarantee that it always loses. as soon as there's any number compared to it, that number will be bigger. Okay, so this is again where we're going to store the, let me zoom in on this because this is what we need here. This is where we're going to store the rolling maximum as we consider each node as possibly the root of the optimal path, right? So it starts out really bad, we'll basically replace it immediately, assuming there are already nodes. Okay, now I'm just realizing we are going to need a helper function because I've defined this in here and I don't want to keep redefining it, right? So we'll say def, we'll just call it max path sum helper, and it just needs to take a root, I think. Okay, the base case is if we have no node, so if not root, we can return 0. And again, what that return value represents is what's the best that we can do without branching on this side, right? From this node, you know, I'm going to calculate the best that we can do if we do branch, put that in branching max. And then we also need to calculate, well, what's the best that we can do if we don't branch, so I can pass it up to my parent node, right? And then it can do something with it. Okay, so if not root, we'll return 0. Now we need to go ahead and get the best that we can on the left. So I'll say the left max, and we have to like actually finish these before we can move on. So I'll say left max equals max path sum helper with root.left, and we're already catching the none situation in this base case right here, so we don't have to worry about like none checking that or null checking that. And then the right max is going to be what's the best that you can do on the right. Okay, and then here's where it gets a little bit tricky. Again, the two main steps that we have to follow, we have to say, what if the node that I'm currently looking at is the root of the optimal path? Okay, if it is, then I'm going to try and update branching max. So I can say self.branching max is whatever is bigger between what it currently is. In fact, I'm going to do some indentation here. So what is bigger between what it currently is and, okay, here's where it gets really ugly. If the left max was if it was negative, so like in this situation for the 15, the best non-branching path you can get on the left is negative. And again, that's just like, why would we ever take that? That's never going to contribute to our sum. It's always just going to make it worse. So I'll make this whatever's bigger between left max and 0. And so this basically just guarantees that we won't add negatives, right? If it's negative, just add 0 instead. Okay, and then the self, like the root value. Okay, and then we'll do the same thing on the right. So if there is, if there's a negative number over here, let's not take it. But if there's a positive number, then we'll take it, basically. Okay, so now we're updating that rolling maximum to say like, hey, assuming this is like the true node, the true root, then let's go ahead and set the branching max to that value, the best one that we've seen so far. And then again, what we need to return is, the best that we can do without branching. So that would mean, like, for example, at 20, this is going to be like, let's choose 15 and 20 instead of 5 and 20. Now, if they're both negative, then we just return our own value, right? Yeah, I suppose I should say if both of the children return something negative, then I'll just return myself. There's no reason to make that value worse by choosing one or the other. Now, here's where it gets weird, though, because we can't just say, like, since the root here is negative, for example, if that was the only node, we can't just say, oh, don't return anything, because we were told in the problem prompt, like, there will be at least one node. You'll have to at least choose one. So we can return, I guess I'll say root.val plus whatever's bigger between left and right, and if they're both negative, let's not choose either. So we'll just say max of left, right, and 0. All right, I think that it feels good. Okay, so I think that's it. This, I think, covers all of the algorithm steps that we talked about over here. Return the best we can do without branching, yep, which is this. So pick one child, left or right, pass it up to the parent to see if that's a better root, and so on and so forth, so you get to the top. So then when you get to the top, just running this function is going to have branching max be as high as it can be. Which makes me think, is it possible for a non-branching... My gut is saying that a non-branching path is never going to beat the optimal branching path, because the branching path includes, like, the like both children, or it won't include a child if it's not optimal anyways. So my hunch is that if you just run this, so I'll say max path sum helper with root, and then just return self.branching max. I think this should work. We might be confronted here with a base case where it we need to return the non-branching sum. If so, we can just return whatever's bigger between these two. But I think this should be fine. Let's find out. Ooh, I'm gonna mess up here. Oh, sorry. This should be wait. Name left is not defined. What? Return root.val plus oh, this is left max and right max. Okay, that looks good. Okay, great. So my hunch was correct. Yeah, since the branching maxima here, they already take into account the possibility of like ignoring one or both children. So we, at the end, we don't need to actually deal with the overall return value here. It's just like, yeah, we already considered all the possibilities down below, so now we can just return whatever got stored there. Yeah, so you could do this without the class variable. I think the class variable is probably the cleanest way to do this. You could also do it as a function variable and then just use non-local branching max right here. The last thing you could do here, which I think is kind of evil, I wouldn't do it this way, is you could pass up a tuple every time. You could pass up what's the non-branching max and what's the best branching max we've seen so far. I think that's like unnecessarily complicated. Like, we always want to just replace it anyways if possible, so I think this is probably the better way to do it. It helps us from having to like do weird like index related like accesses and stuff. So yeah, I'm surprised that we got through that, because every time I've done this problem in the past, it has kicked my butt, frankly. Not like overall, I get the overall algorithm, but it's always the weird like, hey, should we take this path or should we not take this? Like, should we add a 0 here or no? I always like end up fucking that up somehow. But it worked out this time. It's actually pretty short as solutions go. So let's just talk about complexity. So the time complexity here, we're gonna have to look at every node exactly once. We don't have to like resum the subtrees. So O of n time complexity. Space complexity here, there's no, well, we have constant additional storage with this single like numeric variable. But the bigger concern is the recursive overhead, which is going to be O of log n, because, you know, we might have as many layers active as one time as the height of the tree, which is log base 2 of n. So not too bad. Yeah, once you boil it down to kind of the overall concepts here, it's pretty manageable. So that was fast. We did a medium problem in twice this time, so I feel pretty good about getting through it. Sweet. We're gonna call it there. I was just reminded, I completely forgot that we have a GBM tomorrow night. So if you're tuning in tomorrow, this session will be at 6 p.m. and then the GBM will be at 7 p.m. And it's going to be another tree problem. And I think for the GBM we're doing trees and also heaps, but low-key we never got to heaps. So we'll just talk about them because there's one, I think, heap problem in the Blind 75. Anyways, that's what I got for y'all. Have a great night, and I'll see you maybe tomorrow.